Welcome to learning module number 4, Mechanical Properties of Metals. Metals typically exist in one of the following shapes: sheets, plates, tubes, cylinders, rods, discs, wires, channels, and cups. Now, to get metal into one of those shapes, we use the following metal forming operations. They include casting, rolling, forging, extrusion, and drawing. Now, depending on which operation the metal was subjected to, defines the final metal's properties, such as the metal can be stiff, the metal can be strong, the metal can be ductile, and depending on which operation it was subjected to, those properties can be manipulated and changed. Now let's look at each of these operations one by one. Casting. So, the process is the following. First, the metals are melted in a furnace. Then it's an optional step, but now since we are familiar with alloys, it is listed here. In case if you would like to produce some kind of alloy and you need to introduce the dopants, right, or impurities, then alloying elements are added and thoroughly mechanically mixed. Just as an example, magnesium is added to aluminum to produce a stronger and lighter alloy. Once mechanical mixing takes place, oxide impurities and all unwanted gases are removed. And then the final step, the melt is poured into a mold and then chilled to solidify. So this is big picture wise, right? So we liquefy something, right, the metal, and then the optional step, we introduce certain alloying elements, we mix it very well, then we get rid of oxide impurities, we get rid of all unwanted gases, and then we pour it into a specific mold, right? And of course, the shape will be changing. Here's just like the image of something that it actually looks like, right? This is a liquid metal that is poured into a mold. And then you can produce intricate shapes, let's say like that. Once it is in the mold, then we just leave it to chill and to solidify. But what happens at the molecular level, right? What exactly happens when the material solidifies? All right, and so usually there are several steps that take place. First, I would like you to envision the liquid metal, and this is going to be all this bluish light blue color represents the liquid. Now, once we allow the material to cool, right? So basically, once we remove the source of heat, we will see a bunch of nuclei being produced. And these are the dark blue dots. Something to keep in mind is that these nuclei, they can once they start growing, they can actually continue growing, and then they can form these crystals like this, right? Or sometimes they get redissolved and the new nucleus forms. Okay, so it's kind of like let's describe it as a dynamic process, right? But those nuclei that successfully grow into crystals, then as solidification proceeds, they continue to grow. And eventually, as they continue growing in size, they will touch another crystal, right? And this is how you end up with grains, right? And I'm defining it kind of like trying to shade it for you guys. And then all of those grains will be separated by the grain boundaries. And if we ought to look at the crystal, not the nano, just any crystal, under the microscope, you will see something like this, right? And you can clearly see that these are examples of grain boundaries, and these grain boundaries, they separate the grains that formed during the solidification of the metal. Okay. So So this is something that is relevant to the casting, right? This is how exactly how the material forms. Now, the next step is called rolling, okay? So what usually happens is that we use very strong and very hard rollers, and the whole purpose is to reduce the thickness of the starting material. The starting material, and you guys can see here in the image right here, we usually start with an ingot, and this is how we call it, right? This is going to be an example of the ingot. And then the idea is that we pass it through the rollers, and as we do so, we reduce the thickness of the material, and this allows us to produce the plates and the sheets, right? Now, typically, the process is performed in many passes, and as the thickness is reduced, keep in mind that the length will increase, but there is something that will remain constant, and that is going to be the volume, right? So, in a sense, if any of you are experienced with cooking and if you've ever made pasta from scratch, right? In a sense, this process reminds it because you start with dough, right? Something that is very, very thick. And as you pass it through the rollers, you actually reduce the thickness, right? With every single pass. But the volume, right? The volume of your starting material always remains the same, right? It just what happens is that the material elongates, right? Now, something to keep in mind is that the rolling as a process can be done at room temperature, and in that case, we call it a cold rolling. There's going to be a very specific difference between the two. Or it can be done at very high temperatures, which we call a hot rolling. Depending on which process you proceed with, will change the material drastically, and I'm referring to materials properties. Okay, so just a little bit about the hot rolling right away. So typically, whenever we apply the hot rolling, right, the material is heated to high temperatures, and those temperatures we typically call recrystallization temperatures. Now, the reason sometimes we opt out with hot rolling mostly is because it allows for an easier and greater reduction of thickness in a single pass, right? Due to the temperature, it allows us to basically reduce the thickness a lot more, right? Because it requires less force, less energy, right? Um, for example, for steels, typically the ingots are preheated to about 1200 degrees C prior to rolling. And the hot rolling process looks something like this usually. We use a series of four rolling mills, and we do that to continuously reduce the thickness. Now, cold rolling and the difference with the hot rolling. Whenever we are applying a cold rolling, the temperature of the work is significantly below recrystallization temperature, and typically it is done at room temperature. And of course, in these circumstances, it is a lot more difficult to cause the plastic flow, right? There's going to be a lot more friction, and that means we need a lot more force to cause the plastic flow, right? Meaning that it will require higher power to cause this plastic deformation, right? Now, in every single pass, you will achieve less thickness reduction if we ought to compare cold rolling to the hot rolling, right? Now, what is very important, you're probably now wondering, but then why? Why would I opt out with cold rolling if I am to think in terms of efficiency, I cannot reduce the thickness as fast as I could do with hot rolling, right? It requires more force. That means requires more power, energy, and obviously cost, right? So question is, why would I even go with cold rolling? Well, because it offers you exceptional benefits. First, is that material, we call it strain hardens, and I'll tell you later what exactly it is. But for now, you should keep in mind is that once you subject the material to cold rolling, you actually make the material a lot stronger. This is not something you can achieve with hot rolling. So once again, if you take the ingot, right, two identical ingots, and you send one to hot rolling and another one to cold rolling. And if you would like to reduce the thickness by 30%, okay, you will achieve that a lot faster with the hot rolling, right? You will need less passes. It will require a lot more force, time, to do the same reduction in thickness with cold rolling, but cold rolling will yield you a material that is actually stronger than the original material that you submitted to the process, okay? Something that you cannot achieve with hot rolling. Now, but there's always a price. There's always this fine balance. Even though you make the material a lot stronger, the material also becomes more brittle. And if you guys remember, that means that being brittle, that means that it is not ductile anymore. Okay. Now, there is a way to improve ductility a little bit. Sometimes after the cold rolling, we can actually apply reheating because it may allow us to improve ductility. Another thing is that cold rolling also allows us to achieve an excellent surface finish. And sometimes for certain industrial processes or for certain products, it is beneficial, right, to have this beautiful, excellent surface finish, something that you can actually see on the image there, right? This very characteristic metallic shine. Perhaps now that we know the difference between the two, question is, if you plan to make cast metal sheet, ooh, that looks like that doesn't sound English, right? Let's reword it a little bit. If you plan to make metal sheets from ingots, right? So I would like to take ingots, right? And perhaps they were made with cast method, right? So I have like this cast ingots and I'm trying to make metal sheets out of those, meaning that I would like to reduce the thickness. Question is, do you want to use hot rolling first or cold rolling first, and then why? Okay, so for this particular question, you have to go with both, okay? And then this is how the process works. Specifically for your process that has been designed, they're using both. So the question here is the order. If you were to use hot rolling and cold rolling, which one you would actually use first and why, right? So typically, the hot rolling is applied first, and many of you may guess it. Why? Well, because it is more efficient in reducing the sheet thickness, right, than cold working. It will allow you to get to the thickness that you're looking for in very few passes, right? And later, you can pass it to the cold work, right? If, let's say, you would like to manipulate the strength of the material, right? If there's a specific number you would like your material to get to, right, in terms of tensile strength. Sometimes the rolling process looks something that is demonstrated here. What happens is that at every single set of rolls, you achieve a reduction, right? Let's say you start with 50% reduction, then you go into 40% reduction, 30%, 35, and so on and so forth, right? Think of it as a series of the rollers. Now, whenever we are to apply the cold rolling or the hot rolling, well, specifically the cold rolling, right? We actually can estimate the percent of cold work that is required to achieve the desired reduction in thickness. And so the equation here, I'm gonna shorten cold work to CW, right? And then the equation here is going to be initial metal thickness minus final metal thickness divided by the initial metal thickness, and we will multiply by 100 to get to the desired units, which is percent, right? So it looks like I would have initial thickness, which is going to be x sub naught, minus the final thickness x, and divided by the x naught. times 100%. We can also have a shortcut in a sense that you can have delta x, which means the reduction in thickness, right? Divided by the original thickness and again multiplied by 100%. I think we have a few example problems where we can actually apply the math to the real world problems, okay? Let's look at this problem. We're looking at the brass sheet, which is 0.0955 centimeter thick and is cold rolled with a 30% reduction in thickness, okay? So you are looking at the final thickness, right? This is your X. Oh, what must be the final? Hold on. This the cold work has not been. I take it back. Take it back. We are looking at the X naught, right? So we have a sheet with a specific thickness, and then it will be cold rolled with 30% reduction in thickness. We need to find out what is the final thickness of the sheet, right? So we're looking for the X. Let me remind you for the equation, right? It was X naught minus X divided by X naught times 100%, right? I don't like carrying the percentage. So instead of putting 30% for the cold work, I'm just going to put 0.3 because it's going to make the math a bit easier, right? What I'm going to do is at first, I'm going to solve the problem and I need to find this X, right? The final thickness. So first, I'm going to solve the problem using the equation, and then I will show you the shortcut because for certain problems, it is always easier to go with a shortcut. Okay, so my x naught is 0.0955 minus x divided by 0.0955, right? So that would give me 0.3 times 0.0955 equal to 0.0955 minus x. And then I'm gonna transfer it here. 55 equals to minus x. And this would look like minus 0.7 times 0.0955 equal to minus x. And then your x getting rid of minus on either of the sides, and I will do the math right with you together to encourage you do it together with me. I'm actually doing it using a calculator, right? Times 0.7. And it looks that the final thickness is going to be 0.06685 or 669 if I am to keep the same amount of significant digits as the in the example. But this is the final thickness. So basically, if you are to begin with the sheet with this thickness, right? And if you ought to apply 30%, you will end up with this thickness, right? How do I apply a shortcut, right? Well, since I know that I begin with 0.0955, right? And if I am to apply 30% reduction, that means I will be left with the 70% of that. So to find the 70% of that, you can just find the percentage, right? And if you ought to do the math, you will find out that the number is going to be exactly the same, right? And I will highlight you here, like this is what I mean by the shortcut, right? So if I am to put it here as a shortcut, you actually at some point arrive to this line when you do the proper calculations. For certain problems, I do recommend using the shortcut, especially if you're very good with the concepts and percentages and things like that. For examination problems and for more complex problems, I do not recommend going with a shortcut because this is how mistakes happen. Now, before I move on to the next problem, I do have a recommendation because it's a very common mistake that happens. Before we move on, we need to look at the answer and think just for a second, well, does that answer make sense, right? So I'm giving the initial thickness and I'm applying a cold work, meaning that I'm reducing the thickness. That means that the final thickness or the answer that I arrive to should be less than the initial thickness. In our case, that is what you would expect to be. So now we can move on. The reason I'm bringing it up, because in the examination, for some reason, we often end up, even though we are applying cold work, but sometimes people submit the numbers that are larger than what they began with. Mistakes like that happen, and this is why I would like you, before moving on to the next problem, take a step back and look at the number that you arrived to, right? And ask whether it makes sense or not. Let's look at a bit more complex problem, right? Let's take it to the next level. Okay, so this time we are looking at the sheet of aluminum alloy, which is cold rolled 30% to a thickness of 0.08 inches. Okay. If the sheet is then cold rolled to a final thickness of 0.064 inches, what is the total percent work done? This is the key word here, okay? So it looks like I am doing it in two steps, okay? I begin with something that I don't know the initial thickness, right? But I know that once I applied 30%, I arrived to 0.08, right? Then I apply unknown amount of work and I write to the final thickness. So if this is my final thickness, right, this is going to be my intermediate thickness, right? So why don't I put it as xi, and here it actually doesn't won't even matter, right? But keep in mind is that this is the final thickness going to be right here. So what is the proper way to do that? Okay, well, for us to estimate the total percent work, we need to find out what the initial thickness was, right? Because I know the final thickness, but I need to find out what the initial. How would I find the initial thickness? I can use the knowledge about the first step, right? It says that we've applied 0.3% cold work to a thickness. So we had some kind of X naught and we arrived to 0.08, right? This is the number here and x naught. So again, 0.3 x naught minus x naught is equal to 0.8. That gives me 0.7 x naught equal to 0.08. The final thickness is going to be 0.08. My apologies. The initial thickness is going to be 0.08 divided by zero point 0.7, right? Looking at the number here, and I'm going to keep, since the question keeps three significant digits, I'm going to stay consistent with the author, and I will keep three significant digits, right? So this is my initial thickness, 0.14. 0.114, okay? Before I'm moving on, I need to make sure that it makes sense. The number is greater than the intermediate number, zero point 0.08, and that makes sense because I had to start with something thicker. Once I applied my 30%, I got to 0.08, okay? Now, my second step would be, and I would like to preserve some space, so allow me to make it slightly smaller. I would like to remain on the same side. Now, next step is relatively simple. To estimate the total percent cold work, I'm going to do the initial thickness minus the final thickness, right? Divide by the initial, and that shall give me, okay? So that looks as, I'm gonna, okay, so why don't I multiply it by 100% right away? And the answer here is going to be 83.9, right? 83. Well, 30%, let's just round it up. I'm rounding it up to 44%, right? 44%. All right. So 44%. That is our final answer, right? The total work. All right, before I move on, I know that at least one person in the audience would think, why would we do that, right? If I know that 30% was applied first, and I know the numbers for the second step, why don't I just find out how much work has been done in the total step, and then I just sum things up, okay? And before I do that, I would like to do that, so you will see what will happen, right? I'm gonna say this, do not do this, okay? Or perhaps never do this. And I'll give you an example. So once again, you may come up with an idea that, okay, well, I know that the first step was 30%, and then I have everything to calculate my second step, right? So what you could do is that you can take this number. So I'm just looking at this two, right? The second step. And again, I will multiply it by 100%, right? 0.08 minus 0.064, and I divide by 0.08. So that would give me actually 20%. And then you will say, well, okay, first step was 30%, second step is 20%, and the answer is 50%. And then you report this answer, and you will be losing a lot of points, right? This solution is wrong. Well, why? Because when you estimate this 20%, right, and then later on you add it, you assume that 0.08 is your 100%, but that's not true. We know that the 100%, the number is that we found it earlier, and that is actually right here, right? So please be very mindful not to make a mistake like this. In your homework or any other graded assignments. Okay, so we're moving on. Excuse me. Next process is called extrusion. So once again, up to now we covered forging. Oops, take it back. We covered casting, and then we did rolling, which has two types, cold rolling and hot rolling, right? Next process is called extrusion. So what happens is that usually we take a metal workpiece and we call it a billet, and then we use it to reduce the cross section, right? And the way it is achieved is that we take the billet and we force it through an opening in a die under very high pressure. Okay, so usually this is performed at high temperatures. And something to keep in mind is that there are two ways to proceed. There is a direct extrusion and then there is an indirect. So I will try to show you the difference, okay? So this is going to be our direct, and this is going to be your indirect extrusion. Okay, so the difference is kind of slight, but hopefully I'll do a good job explaining the difference. So this is my billet, right here. So, and what's going to happen is that I'm going to use this ram, right? And I'm gonna push my billet, right, which is at the elevated temperatures, and I push it through this opening right here, right? So let me just highlight this die for you. You have this die, and it means that in between there's a specific opening, right? And of course, I can change dies depending on which configuration I want to achieve. But this is going to be the final product, right? So I'm kind of like ramming my billet through the die, okay? Now, that's a direct process. In the indirect process, your billet is kind of stationary, right? It is still at elevated temperatures, but it is stationary. But what is actually being moved is the die block itself, right? So you have a ram, and then as you push it through the billet, you will have your final product right here. You guys can see this is the product right here. So this is the difference, right? But what it means is that usually in the indirect extrusion, right? So this is the extrusion right here on the right-hand side. In that process, there's the friction is usually lower on the billet and therefore needs less power. However, it does have a limit on the applied load. Okay. Now, we usually use extrusion when we would like to produce such products as cylindrical rods, tubes, and it could be metals with some irregular shapes. I'll give you an example. Let's say you need a metal that has like a shape like okay, well, you guys get the point, right? Or it could be a metal where you would like to have a shape like this, but very irregular shape. And the way you can achieve it is that if you have a die that have a very specific shape, right? And as you push the billet through it, it allows you to produce that desired shape. Extrusion may use lubricants, right? And it kind of makes sense. If you wish to look at the real-time process, I'm sharing this video with you from YouTube. Just follow the link. And I think they are showing their quite intricate metals, but then it will kind of like make sense what the extrusion is. But in short, it would be forcing the metal through the die, right? And a die has a very specific shape. Forging, okay? Hopefully someone recognize this guy. This is Andre from one of my favorite video games. So, and I thought this is probably the best way to actually introduce what the forging is, right? So, metal is hammered, right? Which means a dynamic repeated blows, or it can also be pressed very slowly, usually increases the force and it is slowly pressed into a desired shape. And typically we use different dyes, right? Because that's what allows us to shape the material specific way, right? And those dyes, they can have they can have a different geometry, right? And that is either open or closed. In the open die, the dies are either flat or simple in geometry, right? And you guys can see this is an example of open dies that they are either flat or they have very simple geometries. Or a closed die, these are the dies that have upper and lower impression and they are very, very like a lot more complex. Here's going to be an example of something like this, right? So what's going to happen is that once you pour the material in there, right, you close the die and then you apply the pressure, okay? Or you can actually hammer the material, right? That's exactly what this man has been doing for my armor that I used to play the video game. All right. Now, something to keep in mind is that cold forging, right, improves structural properties. And in a sense, the concept is very similar to the cold work itself. It also removes porosity and increases homogeneity. And it looks like I have a video for you as well. And unfortunately, I do not recall what exactly I've included in that video, but please be curious and check out that video. It has to be good if I included it. Now, the next process is drawing, okay? So, we need to keep in mind is that there are two different processes. I almost jumped too fast. There's wire drawing, and then there's also a deep drawing. Okay, I'll start with the wire drawing. So we usually start with a rod or a wire, and then that rod or wire is drawn through several drawing dies to reduce diameter, right? So that's what it usually looks like. The key word here is that the way wire drawing is different from the cold work is that in cold work, we are reducing thickness. And then in wire drawing, we actually reduce the cross-sectional area, right? So we reduce the area. And keep in mind that the volume remains the same in either of those processes, right? We elongate, right? In this particular example, we will be elongating the rod or the wire. Now, what it means is how would I estimate the percent cold work for the wire drawing, right? The equation will change a little bit because the concept is a bit different, right? There's a reduction in area. This means is that in here, I will have change in cross-sectional area, and it's going to be A naught minus A divided by A naught times 100%. And I'm trying to recall whether I have, before I jump to further slides, yep, I will actually introduce it here. Now, I want you to think of the wire and I want you to think of the cross-sectional area, right? What the area will actually look like. It's going to look like this, right? And now hopefully people remember that the area in this example is going to be PR squared. Or if I am to use the diameter, right, that means it's going to be P diameter squared divided by 4, right? Because the radius is half of the diameter. So now if I am to plug it in here, and I will do it P d naught squared divided by 4 minus P d squared divided by 4, all of this divided by P d naught squared divided by 4, okay? Allow me to enlarge. Now, if I am to take pi, I bet I was saying p all the time. If I am to take the pi over 4 out in brackets, right? If I factor it out, I can get rid of it. And that means that my entire formula simplifies. I'm just trying to, as I keep saying, it's a reduction cross-sectional area. But sometimes calculating the entire cross-sectional area is just doing an additional work. And so I'm trying to just simplify it to a measurement that you can actually get very easily and use it right away, which is going to be the diameters, right? So it's going to be diameter squared minus d squared divided by the initial diameter squared. And obviously you multiply it by 100%. And this is how we find the percent cold work for wire drawing process. I'll say it right away. Most common mistake that I see among students is that not recognizing when to use thickness, when to use diameters, right? So meaning that you need to recognize the cold work, right? The cold rolling versus the cold, the wire drawing, right? So once again, the rolling process versus the wire drawing, right? Because for the rolling process, we measure the reduction in thickness, and then for the wire drawing, we measure the reduction in cross-sectional area. Okay, so sometimes I give students a problem where I clearly describe the wire drawing, and then they operate. So what happens actually is that they use diameters, but they forget to square it. So this is perhaps where I'm going to, right? So please keep in mind is that this is important, because if you skip it by accident, and this happens a lot, and I understand where the mistake comes from, the solution would be off, right? And the reason we're using square diameters there because we are looking into the reduction in cross-sectional area. All right, now deep drawing. We won't be doing any math for the deep drawing, but it's important to understand. So because I did mention it in the first slide, I believe, right? If you guys remember when I was mentioning all those functional shapes, one of the shapes that I mentioned was a cup, right? And you actually do the deep drawing to produce this cup-like components, right? We usually begin with flat sheets, and then the way they are deformed into cup-like components looks just like this. I have this beautiful metal sheet, right? And what happens is that it is fixed, and then I'm going to use something to punch my metal sheet, and this allows me to produce a cup-like shape. Okay, and that is it is also called deep drawing, right? It's just the difference is that this is deep drawing. Okay, let's look at the example problem, and I think this example problem is for the wire drawing. Yep. So the key word here is a brass wire is cold drawn 25% to a diameter of 1.1 millimeter. It is then further cold drawn to 0.9 millimeters. What is the total percent cold reduction? I intentionally give you another problem to make sure that you do not make the mistake that I described earlier, right? Where you can overestimate the total percent work. Okay, so that means that I'm going to go with two steps. I do know my final thickness, right? But I need to find out my real initial thickness. So if I am to proceed with the equation, it looks like 0.25 would equal to d naught squared. This is very important, not to forget this squared, right? Minus d, well, perhaps since I started doing it this way, well, um, I'm gonna plug in, my apologies, I'm just trying to start plugging in the sum of the numbers, right? D naught squared. So in here, that would be what? 0.25 d naught squared minus d naught squared. That is going to be 0.75. I hope you guys are okay with me skipping some of the steps, just for the simplicity. And then I'm getting rid of this minus and minus sign, and then my d naught is going to be the square root of 1.1 squared divided by 0.75. Now let's see what the initial diameter was. And if I am correct in my math, I know that that number has to be above 1.1, right? Otherwise, it won't make any sense. So I will have a square root of 1.1 squared divided by 0.75. Okay, the answer is 1.27 millimeters, right? So that is actually the initial diameter. Now that I know the final diameter, I can jump into estimating the total percent cold reduction, right? So the cold work is going to be 1.27 squared, right? Minus 0.9 squared, divided by 1.27 squared multiplied by 100%. And if we are to do the math, well, I will do it with you to motivate you. Use your calculator together with me. 1.27 squared minus 0.9 squared, and that value is divided by 1.27 squared. And I messed up by accident. I pressed some kind of wrong button. So I'm a little bit behind now. 1.27 squared, and hopefully at this point, multiplied by 100%, 49.7, right? That is the cold work. Or it's okay if you ought to round it up and report it as 50%. But that is the answer for the total percent cold work reduction, right? Okay, moving to the next concept. So now I would like you to think about it. Okay, so I take a metal and then all of a sudden, in a sense, I squeeze it, right? I can either like squeeze it through something, or what I do is that I apply like, if I am to describe what happens to the metal, is that I'm applying a motion like that, right? Because I'm trying to like elongate the material and reduce the thickness in either of those, okay, in some of those processes, right? Because casting doesn't include a step like that, right? But what happens at the atomic level, right? Let's get down to atomic level. Because if we are to apply a certain force, right? If we are to apply stress to the material, there is always a response, which we call strain, right? And let's look exactly what happens. So once the force is applied, the metals undergo deformation, okay? And I want you to look at these images right here. What happens is that I want you to think of a bar, of a metallic bar, and imagine that they are fixed on both ends. And what happens is that I'm applying the force and I'm stretching it upward, right? And because I'm trying to imitate the same motion, right? Just like this, like you would do in cold rolling or wire drawing, right? Now, the deformation can be of two types. First is the elastic deformation. What happens here is that the atoms elongate, like in a sense, think of it as the atom is actually stretched, right? And what happens is that, of course, the overall specimen also elongates, right? But the important thing is that the atoms return to the original dimensions once the force is removed. And this is why when we say elastic deformation, think of the rubber band. That's exactly what happens, right? So we elongate and the atoms actually stretch, right? And that's why the entire material stretches. But if we are applying only elastic deformation, if I am to release the force, the material, excuse me, goes back to its original shape. And this is why we call it recoverable deformation, right? Meaning that you can still, in the process of elastic deformation, you can still go back to the original shape. Now, with plastic deformation, that's a bit different, and just spoiling it for you, there's going to be a slip, right? So you can't go back. Once the slip happens, the material has been deformed permanently, right? So basically, what happens is that atoms break bonds, right? Or perhaps I should say that the bonds between atoms are broken due to the force that has been applied to the material. And then the atoms slip on each other. And you guys can see it right here. If you draw a line right here, you don't see a step, right? Because what happens is that the metals they just elongate, right? But then they go back to where they are. And in here we can see a slip right here, right? And that slip occurs is because the bonds between the atoms are actually broken. And once that slip occurs, I feel like I have a dead spot on my screen. Once the slip occurs, the atoms can no longer return to the original positions, meaning that this is permanent deformation. Your material will look a little bit crooked, right? Forever, right? Because that deformation is now permanent. So is there a way to quantify it? Of course, and let's go over it. Well, so what we are referring here is a normal stress and strain. And when I say normal, I want you to just keep in mind is that whenever we say normal, that means that the stress is perpendicular to the material. So if I am to take a bar, right, and if I am to fix it, and if I am to apply a normal stress, that means I'm stretching it, right, upward, or I'm pulling it to the sides. This is going to be a normal stress. Sometimes we also call it engineering normal stress, okay? Now, I'm going to use the letter sigma, okay? This is what I defined for engineering normal stress. And the way you find it is that you have the force. Usually force is something that you can control. And this is something in most experiments you can actually estimate it. This is number you usually know. And then you divide it by the cross-sectional area, right? So an example of the cross-sectional area is going to be, well, this is going to be your cross-sectional area. And this is something that we've already seen before. It's going to be pi diameter squared divided by 4, or if I am to use the radius, it's going to be pi r squared. The units of stress are either pound per square inch or Pascal, right? And hopefully that makes sense. Uh, um, because you want to have the force divided by the unit of the cross-sectional area, which is either inches squared or meters squared, right? Now, the strain, and we're using the letter epsilon, is the response. And I want you to think for a second, once I am applying this normal stress, right? Once I'm stretching the material, what happens to the material? The material actually elongates, right? And I can calculate it by calculating or estimating engineering normal stress. And the definition is that it is a change in length divided by the original length, right? So that means you will have L minus L naught divided by the L naught, or delta L divided by the L naught. And sometimes if we would like to, we can either have it unitless, or we can, sometimes you will see me occasionally saying 5% elongation, right? So sometimes I would actually go with percentage units. You'll see examples like that. But typically the units of strain are dimensionless, right? Because you have units of size divided by the units of size, right? And once again, the sigma and the epsilon, right, are referred as normal, right, either engineering stress or strain, because they act perpendicular to the surface and then they cause the change in length. Okay. Let's solve an example problem to right away. I just saw something. I saw that the subknot was gone from the slide, right? It's the change in length divided by the original length. Okay. Now let's look at the problem. A tensile specimen of cartridge brass sheet has a cross section of and a gauge length of 2 inches. Calculate the engineering strain that occurred during a test if the distance between gauge markings is 2.35 inches after the test. I'm going to draw something for you so it makes sense what the gauge is. So guys, you had some kind of brass sheet, okay? And you do have dimensions here, but this is something that is, at the moment, it is irrelevant, okay? But this is what you had before, right? And then think about it. You had a gauge, right? So you had basically, well, easiest way to explain it is that you had two grooves, and you knew that the size between these two grooves was 2 inches, okay? So now what's going to happen is that I'm going to fix it with like clamps, right? And I'm going to apply the force. And what happens is that the material elongates. We don't know how much, it doesn't really matter. Well, it's about to matter, right? But once you elongate it, now you're taking this material out and you see that the distance between your gauges, let's say it's now like this. And all of a sudden, you take a ruler and you measure it and you find out it's now 2.35. Okay, that's exactly what happens. This is the knowledge we're given. And then now, given that, we need to calculate the engineering strain. Okay, well, I'm just going to go by definition. Engineering strain, which is your epsilon, is L, right? The final length minus, or change, perhaps I should say change in length divided by the initial length, right? And so that would mean you have 0.35, because that is the difference, divided by 2, right? So, and we're going to be using the unitless, right? 0.175, right? And since it's inches by inches, we consider it as unitless, right? Or the elongation is roughly 17.5%. Okay, so hopefully that makes sense. Perhaps. Mhm. Now, what I was describing does remind a tensile test, and this is something that, as an engineer, you want to be you want to know very, very well. Okay, so. What is a tensile test? Typically, for us to find out anything or perhaps everything about the material in terms of the strength, the ductility, the yield point, meaning that when the material actually fails, we need to perform the tensile test. Or in a sense, for us to know mechanical properties over any metal or a metallic alloy, we need to conduct a tensile test, okay? So the way we do it, and then first I'm going to show you what you usually see. Once you perform the tensile test, you usually see a diagram like that, where you will have, it's a stress strain diagram, meaning that your y-axis is going to be your stress. Keep in mind the units here are PSI, but multiplied by 1,000, right? So it's not 10 psi, it's actually 10,000 psi. And in here you will have engineering strain, right? So meaning that if I am to apply a specific amount of stress, right, to my material, I can estimate the response in my material as an elongation, right? So how do you usually do it? Well, we usually load our specimen. This is your specimen right here, and we fix it with like holding grips. And then we have a load cell right above, right? This is going to be a load cell. And then what we are capable of doing is that we have a moving crosshead that allows us to to load the material, right? Meaning that you can actually apply the force, that the normal engineering stress, meaning that you can elongate the material, right? And why are you doing that? Well, because eventually you will get to a point when the material is going to break, right? And that means that, okay, so I know the maximum stress that the material can withstand before it fractures, right? Why I want to know that if I'm building a bridge and I know that, well, I will be having that much force on my bridge, whatever is holding the construction has to have a very specific, well, we never get to the fracture point, right? But just giving you an example. Actually, let's go right away and I'll show you what are the key features that you can derive from the tensile test. Okay, so now, first we need to understand that in the tensile test, there is two different regions, and one is a linear elastic range, and then there's going to be a plastic range, okay? So, and I will be drawing everything while referring on the diagram on the right. Okay, so the linear elastic range, and some of you may have noticed it, well, that's going to be this line right here. So you will notice that at some point, there is a linear dependence, right? There's a linear relationship between the stress and this and the strain, right? So, and usually, if it is linear, you can actually use this law right here. That means that you will have your stress is equal to some kind of constant, right? Multiplied by strain. And this is also known as the Hooke's law. Okay, the most important thing that we need to keep in mind about this linear elastic range is that in this range, the generated strain is recoverable. What it means is that if I am to remove the stress, the material will get back to its original position, right? Like nothing has happened to the material. There are going to be no bonds broken or anything like that. But at some point, right, if you are to continue applying the stress, and you can imagine in this test, you just continuously pull the material to sides, you will eventually get to this region right here, which we call a plastic region, right? Now, and the difference between these two, elastic and plastic, is defined by the yield point. The yield point, right? So basically, for now, I will give you just a simple definition, but there is a specific procedure how you actually evaluate that point, right? But I will give you just a short, simplified description for now. Now, the yield point is the point on the curve when the elastic range ends, right? So that means it's like once you have this elastic linear range, and at some point, once it ends, this is going to be your yield point. The important thing is that after this point, any additional deformation is not recoverable, meaning that it is permanent, right? Now, plastic range starts past the yield point, right? And then it ends at the fracture point. And obviously, guys, this point right here, disregard these two. They somehow moved a little bit, right? This is going to be your fracture point. And that means this is the point at which you've applied so much force that the material just fractures, right? It elongates, elongates, and then it fractures. Okay. Now, what else can we get from this from the tensile test? We can also see the ultimate tensile strength, you will notice that occasionally, or perhaps often, I will refer to this instead of saying ultimate tensile strength, I will say UTS. Okay. And this is very, very simple. This is the maximum strength reached on the stress strain diagram. So if I am to look at the stress strain diagram, it looks like somewhere in here, this point is going to be, and you guys can see that this is moved a little bit here. It is right here, right? So this is the maximum strength that that the material can withstand, right? So basically, it represents the largest stress that the specimen can take before fracture. And now, the fracture point, something that I've already shown, it's the point on the curve where the specimen fails, right? So this is kind of the information we can pick up from the tensile test, right? So it's usually, once again, we can see the linear elastic range, we can see the linear range, right? Or I should call it elastic region. There's a plastic region. The two are separated by the yield point, right? The yield point is where the material yields, meaning that from that point on, the deformation that it experiences is permanent. We can also see the largest stress the specimen can take, which is going to be our ultimate tensile strength. And then we can also identify the fracture point. And of course, you can see how much it elongated, right, somewhere in here before the fracture occurs, right? Okay, a little bit more on the elastic region. So elastic region, that is the recoverable linear dependence. And I did show you that in there, it's where you have this line, right? You have a linear relationship between the stress and the strain, right? And it's going to be like this. So if this is my stress, this is my strain, right? Now, what is this E in here? This E is your modulus of elasticity, right? And the best way to think about it, guys, it's the slope, right? By definition, it's the slope. And then that means that materials, they differ, right? And then some of the material will have a sharper slope, some of the materials will have a steeper slope, right? And so what that means is that the higher the bonding strength in the material, right? So the stronger the material, the higher the modulus of elasticity. So if all of a sudden you're looking at the graph and you see these two lines, let's say separated like this, right, two slopes, then which material, what's the best way to show you this? I'll show you like that, right? Um, what am I doing? Let me show you right here. Let's say I have material that looks like this, and I have a material that looks like this, right? So if I am to compare these two, which one has the highest modulus of elasticity, right? Or which one is actually stronger? It's going to be the red one, right? Because the modulus of elasticity here, or the slope, is going to be higher than for the blue material, right? So, and that's how, if I am giving you the diagram with many, which I will at some point in this module, you'll be able to pick it up right away, which material has a higher modulus of elasticity, okay? Just as an example, the modulus of elasticity for the steel is roughly 200 gigapascal. The modulus of elasticity for aluminum is 76 gigapascal, right? And this is why we often opt out for many applications. We go with steel and not the aluminum, right? Because why? Because the steel is stiffer, right? And that means that if I am to apply, if I take both, and if I start applying the same amount of tensile test, right, then steel will not deform while the aluminum will already start stretching and eventually permanently deforming, and it will actually fracture a lot earlier than the steel. Okay, so hopefully that makes sense. Now, the yield point or the yield strength, right? So here's the thing. We already know that by the definition, the yield point is that when material yields, right? It cannot take any more of whatever pressure you apply into it, and it starts deforming plastically, right? Permanently. And the question is, so how do I define it, right? Of course, the prior diagrams I gave you, you may think that, well, it's very clear. Like once you have this change in slope, right? You have a linear, and then you have a line like this, then it's going to be the yield point. But in reality, that's not often the case. And for a lot of materials, you will see that it's very, very, sometimes you cannot explicitly say, well, the point is here. And in general, we should not let people judge by just randomly choose a point, right? Because some people may choose it here, some people may choose it there, but that's a very important point, right? That basically tells you that after this point, the material yields, right? Whenever you build bridges or anything, you don't want anything to start shifting and moving, right? We want everything to actually be able to preserve the structure and the integrity, okay? So this is why there's a specific rule how you define this yield point, okay? And again, the example I'm showing you right now is so clear, and you may think like, why would we do it? Why would even we do that? Because it's kind of clear. But later on, I'll show you the examples where it is actually really hard at a first glance to identify where the yield point is, right? Well, let's take a step back and just go along with the definition, right? So the yield strength is the stress at which a material begins to experience permanent or plastic deformation, right? As I said, the location of the yield point is not always clear, and this is why in America it is different for the UK, but in the United States we use a zero point 0.2 offset yield strength standard. Okay, that is very, very important that you are familiar with this standard. And I'm just going to explain you how you guys are doing it. To identify the yield point using this 0.2% standard, we need to have a 0.2% offset construction line. And I'm talking about this guy right here. So once again, guys, 0.2% is the same as oops, 1 second. Just making sure that it's all visible, 0.002, right? So first you find this number on your strain axis. After that, I'm going to draw this offset construction line that runs parallel to your linear region. So I'm going to draw this line like that. And once I find the intersection, that shall give me the yield point. This is going to be my 0.2% offset yield strength, right? This is the common standard we apply in America. In the UK, it's usually 0.1% offset. But this is how you would do it for any metal using the standard, and especially for the scenario where it's not very clear how to identify. Well, I keep telling you this scary news, and perhaps I'll show you an example like this, right? This is a stress strain diagram for a lot of things, right? And in some of these examples, perhaps if you ought to look at this particular example right here, the bare aluminum alloy, right? You guys can see that in here, it's not very clear. I'll try to do it better way. It's not very clear where this linear region actually ends, right? Because it starts kind of like curving a little bit. So where's the end of the linear region, right? Is it here? Is it here? Is it here? This is why we don't allow engineers to like start guessing, right? Or pinpointing randomly. That's why we have a standard. Another example, a good example would be this anneal titanium alloy, the black one here as well, right? Because you can also clearly see that there is the curve is not as straightforward as you would typically want to have it. This is why you should be familiar with the standard and how to properly identify the yield point, okay? Now, ultimate tensile strength, that already makes sense, right? That is the largest or the maximum stress that reached in the engineering stress strain curve, right? Somewhere in here, somewhere in here, right? Whatever, the maximum point. That should be relatively easy to understand. And then one thing that I want you to keep in mind is that this is what actually happens to the material before it fractures, right? And we call it necking. And what happens is that the material actually the cross-sectional area gets smaller and smaller, and that is important. I'll get back to it, and I'll explain you why this is important. As you elongate the material, right? Well, this is a permanent deformation, right? So once even the sample was taken out from the tensile test, it remains the same way if they didn't let it fracture, right? So typically, necking becomes prominent around the ultimate tensile strength, and it's usually largest prior to fracture, and it makes sense, right? So it's going to get thinner and thinner before it actually ruptures, right? Now, the more ductile the metal is, the more enhanced the necking before the failure. Um, Keep in mind is that stress increases until failure, right? And the reason I'm bringing it up is because if you are to look at any diagram, and I will actually go back to our original diagram right here. If you are to look, well, I added, I'll look at right here. So I want you to see the following. If you are to draw the line with your eyes, you will see that at some point it goes up, 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 and then it dips, right? So you can see the dip. And then you're probably thinking, well, but that doesn't make sense, right? Because I'm increasing, 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 increasing. Why do I see it dip, right? How can I explain that dip? Well, keep in mind is that force is increasing, but your stress is force divided by the cross-sectional area, right? And we always use the original cross-sectional area, but what happens in reality is that the cross-sectional area, due to necking, it actually reduces. And this is why your stress at some point dips, but in reality, the force keeps going up and up, right? And this is why you can see the dip in the stress strain diagram, okay? Um, Now, we can also identify the percent elongation at fracture, right? And this is really important because it's a measure of ductility of a material, right? It allows you to basically understand the maximum elongation the material can experience before it is fractured. The equation is very simple. This shouldn't be there, right? It's basically change in length, final length minus initial length divided by the initial length. The only difference is that we measure it at fracture, right? So we wait for the final elongation, right? Now, since we are also familiar with the wire drawing, the percent reduction in area will give the same information about the ductility of the tested materials, right? And just a few examples. The pure aluminum, the percent of elongation is 35%, whereas if you are to take the aluminum alloy, this guy right here, the percent elongation actually drops to 11%, meaning that it's not as ductile as pure aluminum. And later on, we'll look at the example like this. Why all of a sudden, if you take pure element, it is ductile. But if you are to introduce impurities, right? If you are to make an alloy, the alloys are always stronger, right? And what it means, if there's always a compromise. If a material is stronger, it can be ductile, right? Because the whole point of being strong is to resist this permanent deformation, which is kind of like ductility, right? Now, you can also estimate the modulus of resilience from the stress strain diagram, right? And we call it U sub R. Now, the modulus of resilience is the measure of the amount of energy needed to cause the yield of the material, right? So, So once again, that is the energy that is required to cause the yield. So you're going from this elastic region to the plastic, right? And so of course, the energy is almost fully recovered once the load is removed because we are looking at the elastic region, right? And it makes sense that since we're talking about the energy, it's going to be this area under the curve, which is literally a triangle, right? And this is why the modulus of resilience, it's just the area for the curve, for the triangle, right? So it's going to be 1/2 yield point times uh, um, the strain that corresponds to the yield point, right? Uh, so that should be relatively straightforward. And then the last thing is toughness. Toughness, this is the amount of energy required to fracture the material. So if you ought to go by the definition, well, if that's the energy that are required to fracture the entire material, that is going to be the area, right? The total area under the curve, right? So that means it would also include this little triangle that you saw before, which is the modulus of resilience, right? The energy that is called the energy that allows you to yield the material, right? The rest of the area we added and it allows us to estimate the toughness, right? So that means that the toughness is a measure of combination of both strength and ductility, right? Um, well, that would be a good moment to stop.